So welcome everybody. Appreciate your participation in this second right-of-way asset mapping exchange. And what I'm going to do today is talk a little bit about right-of-way asset inventory and extraction using 4D voxel technology, something that many of you may not have an understanding of. So what I'd like to do is to give you a brief overview of Voxelmaps itself, talk a bit about this concept of maps for machines, then go a bit deeper into the technology understanding of how we collect and manage content, and then speak about 4D volumetric mapping, not just 3D, but 4D, and then address a number of right-of-way use cases, and then at the end, we'll open it up for questions. So history-wise, we're a spin-out from a group called NAVME out of the UK. So it was an established navigation and high-definition mapping company with 16 years experience in doing mapping, had mapped out, I think, 180 different countries in terms of the road network. So pretty significant background in mapping. Took some of the software capabilities and spun that out in 2017, and our two founders actually were two of the founders of NAVME. Worldwide headquarters are in San Francisco. We also, our European HQ is out of Nottingham, England. We also have a European Development Center out of St. Petersburg in Russia, and opened up just recently a new office in Porto, Portugal, for some of the project management stuff. And then we have a team in Mexico City that we just brought in as well to do some additional development. So organizationally, we've got 47, it's probably in excess of 50 people full time. And then we hire a lot of employees on a part-time basis when we have field work. So like last summer, we had 365 part-time people on projects when we had a project driving across North America. And then a number of intellectual property assets that we have as well in terms of filed U.S. patents on some of the technology and pending patents on that, as well as the Simbo mapping hardware that I'll be talking about a little bit later in our mapping platform called VMAS. So let's talk a little bit about this concept of maps for machines. And this is something that we think is really important. So human maps are something that all of us here are really familiar with, right? So these are maps that are on our phone, they're in our cars, they're on our computers, right? And generally speaking, they're there to help us solve a problem of navigation, right? It provides visualization of the geodata. It tends to be 2 to 2.5D. And allows us to navigate to an address. So it could be within a city or a street or even a particular building, you know. And then the data that we use for human maps tends to be a little bit lower in terms of resolution of accuracy. So in the area of like 1 to 3 meters, and it's usually 2D data. Sometimes there are some aspects of 3D, but very little. When we go to the right-hand side here, and when we start to look at maps for machines, it's a very different environment. So we're talking about building models, which are true 3D models of everything we see, like a digital twin of the environment. And we're combining that with really high resolution accuracy of between 1 to 10 meter in terms of spatial accuracies. So just imagine trying to map the world, mapping cities down to 1 centimeter resolution. And it's not about just the location of those objects, whether they be, signs or utility asset poles, etc. But it's all about those features and the measurements and the attribution of those objects as well, right? And by doing that, it creates a platform which really powers autonomy. So whether that's autonomous vehicles or delivery robots or things like automated miniature robots or AMRs or even UAVs and drones, right? Providing that level of accuracy. And at Voxelmaps, we have a pretty unique way of doing that. So everyone online, I'm sure, is really familiar with pixels, right? We're used to using imagery and raster data. But a voxel, is a 3D pixel. And just think of it that way. So we utilize a voxel model, which is kind of a cube, and we create a model of the entire planet and then create a digital twin out of these really small voxels. Think of it as a Minecraft version of the planet, you know? And so Minecraft uses voxels, and many people are familiar with it because of that. However, it's heavily used in the medical community as well, because you can define voxels down to minute individual detail to actually map out brain matter as well in the medical field. So it's widely used across a number of industries. But what's unique about our approach to this whole maps for machines in the voxel structure is this our global approach to the global fixed voxel occupancy grid. So it's basically a mega voxel structure that we create, and it's comprised of multi-resolution voxels across the entire planet. So it's a Earth-centered, Earth-fixed model, which is a standard Cartesian sort of environment with XYZ coordinates, but instead of 0, 0 being null island out west of Africa, this is actually centered on the center mass of the Earth. Okay, so what we do is we place this voxel model in place. Every voxel has a permanent position and a unique address, and then we validate the occupancy status of the voxel. So in this model, basically the voxels, if it's through air, if there's nothing within that voxel, we create a 9-meter voxel, okay? But when it gets down to having objects or feature class within that voxel, we get it down to between 1 to 4 centimeters. So it creates this basically a global, both above ground and below ground, a global geodatabase for 3D and 4D data. And it's a real-time persistent database, supports petabytes at scale. We already have multiple petabytes in storage currently. Okay, so that kind of gives you an idea of the voxel structure. In terms of our approach, in terms of how we manage it. So we have this. What we're our goal and plan is to build this digital twin of the planet. Okay, and it'll be a persistent live model, very accurate, and both indoor, so consuming both internal and external data sets, so indoor and outdoor. It's a 4D temporal spatial database, so we can store data and manage it through time series as well. So we can go back and look at change detection and do automated feature extraction and automated feature change detection across a number of different use cases. And we're also multi-market focused. So working a lot with state and local governments in terms of smart cities, with telecommunications, with GIS mapping, with utilities, robotics, activity in the autonomous vehicles, and even some of the largest tech companies in the world are existing customers of ours. On the collection side, we have the Simbo mobile mapping sensor, and I have a slide that goes into a little bit more detail on this. But basically, this is just a constant collection network of mapping sensors. So our strategy is to have a pretty substantial network of these Simbo devices out in the field collecting data and providing near real-time data collection. So collecting the data, sending that data in near real time to a processing structure that then can do the processing, the extraction, and deliver that information back out to the field in a near real time capacity. And then the data is agnostic to us. So we use, we do mobile data collection, but we have partners that do manned aerial as well as UAVs as well. So it really doesn't matter where the data comes from. It can be incorporated into the environment. In terms of the data insight, so this is the back end of our system, which we call VMAS, and it's a deep learning-based AI recognition engine. And so it supports both 3D and 4D semantic segmentation, basically training objects. So we've already done a lot of training to create, I call it feature class, but basically objects that can be automatically identified, so utility poles, lights, right? Or assets on the poles like conductors or closers, things such as that, okay? And then we have this powerful AI search to retrieve the objects and then perform automatic measurements and then vectorize that and provide that for consumption, whether it's in our product or in a wide variety of other products, like ESRIs or GIS or Autodesk or Bentley. So really agnostic in that approach to in terms of the next. This is just a quick overview of the Simbo. So this is our current version of Simbo. We have a new version that we're taking delivery of in September. I mentioned, this constant collection network. So the plan is to have 70 of these, 70, by the end of the year, and we'll be actively engaged in collecting high definition maps over about the top 100 cities in the U.S., putting those into a spatial database, providing access to that data as a service. So you'll be hearing more about that in the coming months. So we have 6 cameras on this. We also have 2 LiDAR sensors. So we're getting up to about 2.4 million points per second, and we can store up to 15 terabytes on the device. One of the cool things that I like about this is that it's really lightweight, so it's less than 9 kilograms, and it just fits on a Thule bicycle rack. So it's really easy for the individuals that work for us in the field to be able to put this on the vehicle, and every morning put it on, take off, start doing data collection. End of the day, pop it off, put it into its Pelican case, take it in the hotel room. So it's a really quick and easy approach. Some of these, some of the devices you'll see out there on the streets driving, Google, et cetera, well, it'll take 2 to 3 people several hours to set it up. So then you have issues in the evening where you park this thing to make sure. So what's nice as well is that we do a lot of the initial processing on the device. So we have processing capabilities on the device. And then in terms of managing that collection, it's just basically using an iPad. So it's not a heavy footprint and not a heavy investment as well. So we have these for ourselves, but we also sell the Simbos for other customers to do their own collection. So let's talk about this 4D volumetric digital twin that we're creating of the planet. So, 3D maps, are approximate visualizations of the cities, and everybody, is cognizant of this, has seen these data online, but they tend to be empty 3D meshes. So it's really, they virtualize the surface or the matter, and they're not a true digital model of the world. They tend to be low accuracy, and they tend to generalize the structure. So when you zoom in and look at them, a lot of it gets a little bit mushy, right? So it can be a little bit deceiving in terms of the structures themselves. Whereas with the 4D volumetric data, these are a complete data set of a 3D model of all the matter, both surface as well as interior data. Very high accuracy. So as I mentioned before, we're doing collection at the 1 to 4 centimeter level, and then each voxel has multiple time states. So you can have this 4th dimension of time for automating the change detection process. So we have this 3D volumetric measurement unit called the Voxel, and then we provide surface data from the RGB values of the camera or hyperspectral or radar or whatever sensor you have. You can collect the data and provide that as a surface attribution for the particular voxel. We can then take that and do 3D semantic segmentation, deep learning using our AI tools, and extract from that. And then, as I mentioned, these multiple time states that one could then store the data for that particular voxel. Again, we're talking 1 to 4 centimeter voxels, so lots of change can take place, especially in an urban environment across those voxels. And everything is a permanent address. So each voxel has its own permanent address within the spatial database. So it really supports this intelligent search concept to be able to search and perform change detection within those objects. So in terms of the digital twin, that's really what our goal is, to create this digital twin of the planet. So it's, at the city, state, or country level, mapping everything that's visible to the sensor. So again, we're collecting both LiDAR and imagery. So anything that's visible, we're trying to map out and extract as an individual feature. And then the digital twins allow us to access and extract, many different features or assets across various time segments. And then we can convert that into any format as well. So, our customers tend to use geographic information systems. So we just put it in the format that's the easiest for them then to consume. So it may be just a shape file that we provide. Okay. So let me show you really quick what I mean by the digital twin. So this is the initial voxels. We then colorize them, and then we do some initial of the AI segmentation, extract those features, vectorize them as objects. And then once I have that, then I can start, taking the individual layers and manipulating the data. So get it off. I just want the roadways. That's all I'm interested in. Or, roadways plus all the other assets, including vegetation cover, right? So it's a not a simple process. It's a very involved process in terms of the processing, but the technology that we have on the back end with the software allows this to happen in a semi-autonomous manner. And in the future, this whole multi-resolution mod as well. So as I mentioned the multi-resolution voxel occupancy grid, again, the MRVOG, it's multi-resolution, right? So different types of data can be merged together. And so we're merging mobile, we're using aerial LiDAR, access via manned aerial as well as UAS assets, various, EO satellites, electro-optical satellite, visual, or multi or hyperspectral radar. So a lot of different sensor types that can be consumed in the system and then displayed. And some of these images here that I'm showing is actually from some activity we're doing with a group called the Earth Archive Congress that is creating a digital twin of the planet, and we're one of the founding members and supporters of it as well. And then, one of the areas that we're really spending a lot of time in terms of research is just the whole real-time model. So via API access, being able to incorporate real-time data feeds as overlays into the voxel clouds, within the model, and then perform real-time calculations. The software I mentioned before is called VMAS, our back-end software. It's a voxel addressing and mapping system. And it allows the automatic recognition, measurement, and extraction of assets into any required mapping format. So as I mentioned, we have a number of features that have been basically classified as objects in our library, and then the system uses that library to go and automatically classify features. So it could be that if you have some unique features that you need to pull out, we can work with you to do that. We have a customer that we're training next week that is looking at certain types of windows across the city, and so we're working with them, and they'll be training the algorithms to extract windows and be able to identify them as specific types of windows. So lots of capability within that software. And one of the things that it can do is, it can do automatic extraction, but it also allows interactive. So you can actually interactively train the algorithms to extract. Let me just show this real quick. This is a short one. So it's automatically identifying tree as vegetation, right? And then we can go in and identify other features like trunks, right? And so identify that, identify other vegetation that wasn't classified. It'll automatically go through and do the classification. So it's both automated and interactive process, right? And it's all in online web interface tools. And again, these are tools that we use internally. They're developed for our internal processes, but this software is also available to our customers. So whether the customer, acquires one of the Simbo systems, or whether they use their own UAS LiDAR, they can still use our system and the whole virtual reality viewer on the back end to manipulate, consume and manipulate and deliver that content to their customer. So this is going to show you, this is the Embarcadero in San Francisco. And this is just a video showing quickly how hang on a second here, stop it for a second. So basically, we've taken the voxels and colorized it using the RGB values from the camera. And then from that, we can then do the auto extraction. Oops, popped it back to the beginning again. We'll do the auto extraction of the individual features that have been defined in the system, all right? And then you can see here different colors meaning different sorts of features, driving through the vegetation there. And then what we can do then is do measurements on those features. You can see measurements popping up here in terms of the height of the poles, right? And then we can take that data and auto vectorize it and export it. And the same thing on the roadways, like on the right of way here on the road leading to Sausalito. So, capturing all the striping, capturing edge of pavement, capturing light poles, capturing any sort of signage for a signage inventory. So lots of different capabilities to do that in both a automated or semi-automated manner. So what I'd like to do is I'd like to talk a little bit about right-of-way asset mapping use cases. So in thinking about it, I was thinking, when somebody talks about right-of-way, right, what does that mean? Initially when I think originally right-of-way, I'm thinking transportation, but there's a lot of assets that sit within a right-of-way. So it's not just, transportation, it's utilities, it's public works or water and sewerage. So and what do I want to do within that? I want to do a bridge assessment. I want to identify all my drainage features, identify all my culverts, right? Or I want to do a signage inventory or curb and gutter. And within the curbs, I need to find places that need to have ADA compliance. So as an ecosystem, I look at the right of way basically as an ecosystem with potential use cases across a wide variety of different markets. So I'll share with you some of the use cases that we've been involved in at Voxelmaps. So installation compliance. So this was a equipment installation compliance for local government. And so again, you're thinking what I was talking about before on the 4D volumetric mapping, this was critical to them. So they had an existing inventory, and then we went and drove the city's network of roads, did the automatic feature recognition measurements, and then we're able to map new features, new objects back to what had been contracted to be done or what had been licensed to be added, and identifying any areas of non-compliance and provided that to the end customer. Okay, and so one thing I will bring up here is that the delivery and what we provide to end customers is it goes along a pretty broad spectrum. So, and sometimes we're collecting and delivering raw data. That's it. We're just doing the collection and providing raw data. Other times we do the processing, say, of an extraction and classification of LiDAR point cloud, right? Other times it's classification of that point cloud and the extraction of the objects. In other cases, it's all the way to the extraction of the objects and then doing some sort of report or insight generation, right? And that's what is provided to the end customer. So a pretty broad as I mentioned, a pretty broad spectrum of what we deliver. Here's another one of a signage inventory. So we drove a number of roads, many miles of roads, and did a traffic sign data collection and mapping for a major navigation company. So in this case, they were interested in not only extracting the signage, but also doing OCR to identify what is on the sign, right? 7 million signs were mapped, and we did the automated sign recognition. And then for them, we just converted all that data to XML and delivered that. Now, 7 million signs sounds like a lot. So I was thinking last night, and I said, okay, how many miles is 7 million signs? Well, if you had a sign every 15 feet along a roadway, that's 20,000 miles of road, just to give you an idea about the size of this project, okay? Pretty significant. So we have a lot of experience doing very large data collection requirements. So this one, a road network mapping for a major automotive company, we created HD maps for autonomous vehicles. So you're collecting, the road lane model. So you're sometimes driving the roadway several times, traffic signs, striping, all the localization objects to help the vehicle know where it's at, okay? Now, last, I mentioned, the number of part-time employees we had last summer. We did a project last summer in North America where we drove over 650,000 miles of roadway across Canada and the US. 650,000 miles. That's a lot of data. That's a lot of data and a lot of experience, I would say, in terms of data collection. So I would say not many organizations have the experience level of collecting the amount of data that we have from a mobile asset. Asset inventory. So here's another one. This is more in the electrical transmission and electrical distribution. So in this case, utility infrastructure was captured using aerial LiDAR, okay? And we did all the data processing of the customer, captured content, and then this AI, machine learning automated feature extraction, and then validated the assets and created a database of those assets for this particular end user or customer. Vegetation management and encroachment. So in this case, asset capture using both mobile and aerial LiDAR. So you can use both and merge the two together. And we did the data processing of the content and then the automated feature extraction of, the poles, the conductor wires, vegetation, et cetera. And then from that, do a buffer and overlay, a buffer around each conductor line at various distances, seeing where we had encroachment issues on those conductors, and then identified the vegetation, the location, and the amount of vegetation for work order submittal. This was a project we did for a telecommunications company. So this was an interesting one because of the delivery, right? So we had driven a city before, so we had the data in archive, and then this particular telecommunications company had contracted to have a number of new 5G towers placed on pole assets across their service area. So we did this multi-time frame data collection, did the processing, did the AI ML based automated feature extraction. So it automatically identified the location of new 5G antennas. And then we use that to validate the contractor work orders and made sure that they were placed on the right assets as well. So in this case, the customer wasn't worried about, if you look at this image, they wasn't worried about that second pole, right? All they wanted to know was, show me where I have new assets located on what pole. That was it. So an interesting delivery at that point. We've also done some work with another telco on delivery of or creating a model. In this case, we built a digital twin of an area. So we not only did the driving but then we used robots and backpack model to collect the inside of it. So we created a digital twin of this area. And then we ran from their 5G towers, we ran the signal attenuation models within the Voxel spatial database to determine coverage gaps, both external and internal to the customer's facility. So they were looking at not only when people are on the street, but employees in the building, in Office 5G, do they have solid coverage of that And so this just gives you an idea that we just created, each one of these voxels in that space, that airspace, is the signal model. Okay. Let me just show you real quick here. So this just shows a 3D, basically a fly through the model. So you can see the various colors, and the colors are the signal strength of the 5G signal in that particular environment. Okay. And with some of the new 5G signals coming out that can actually penetrate buildings better, having these true models, digital twins, where one can provide the values of the structure type, will be really valuable in terms of doing this in the future. Autonomous vehicles is another area where we're all seeing pretty substantial growth in terms of data collection and capture, especially on roadways and rights of way, knowing where signs are. Are they too close to the road? Make sure people understand, and then provide that, the sign information to people as part of their navigation experience as well. So we recently did an innovative project with a couple of organizations. So, in the existing world of HD map creation, we go out and we do data collection and harvesting via an HD mobile mapping system, right? And then usually what happens is there's so much data here that data gets delivered to a data center. The hard drives are actually delivered to a data center. They then do the processing, and then they can do, this voxel-based AI feature extraction and the vectorization, and then creating that final HD model. Okay. And then at some point, in about a month period of time, additional month period of time, those updated maps are then loaded up to the vehicles database, and then downloaded to the vehicles, excuse me. So you're talking, between 1 month and 6 weeks process in terms of from the time of data collection to the time of updating the vehicle. So we did a process of a project with a couple different companies. One, it was with Verizon and Amazon Web Services. And so Amazon has this Amazon wavelength is basically an Amazon instance, processing instance at the telecommunications facility. So it doesn't go 5G to the telco, across the internet to an Amazon service. It goes 5G to the Amazon wavelength service. So it cuts down, very low latency. The 5G Edge from Verizon is a new, very low latency mobile edge, sort of a 5G bandwidth capability from Verizon. So we had a Wi-Fi antenna on the collection device. We're able to collect the data and do some initial processing on the sensor, 5G the data across the Verizon network to the AWS wavelength instance, process that data. And again, this particular data, we were only processing the LiDAR data because of the real heavy footprint of the image data. So we processed that and then delivered that back to the vehicle. Average was 15-second turnaround. So we went from a 6 weeks period of time in terms of updating to a near 15-second. Now, mind you, this requires 5G services, across an entire network, not just small areas. But the future of safer autonomous vehicles and this vehicle to everything community is pretty significant. If you think about it, I read an article last week and it said that each autonomous vehicle will generate uh, 3 terabytes of data per day, 30 terabytes, excuse me, 30 terabytes of data per day per autonomous vehicle, right? That's 3,000 times the data generated by Twitter each day, right? 3,000 times Twitter each day, one vehicle. So you can imagine the networks that we're going to have to require from the telco side to be able to support that as we move into the future. And I'll just show this real quick. I won't show the whole thing, but this just shows you how much data was being captured. And again, basically each one of these blocks is 200 meters of data. And again, it was updated. Each one of those blocks was updated about every 15 seconds on average. So quite a significant amount of data that we were collecting. So in review, I gave you a quick overview of Voxelmaps, who we are, where we came from. We talked about this whole maps for machine concept and how it's different. It's a different way of thinking in terms of geospatial content. Talked a bit about Voxelmaps technology and how we approach this whole 4D volumetric mapping capability. And then I went over some right-of-way use cases and potential uses of the technology. So with that, I'd like to just open it up for questions. So,
well, thank you, Brian. We have 7 minutes and 7 questions in queue. So let me start right with the first one. Our service area is quite large. What is the largest area you have been contracted to collect?
So as I mentioned, last year, Voxelmaps collected over 1 million kilometers, almost 650,000 miles on one project across Canada and the continental US. So that's about 50 towns around the Earth at the equator. Pretty significant amount of driving. So we can handle pretty large data collection projects and have experience with doing the project management and operations. And I think that's one of the key things. We got some really stellar employees on the project management and operations side of our organization.
Great. We have invested heavily in LiDAR processing. If we have you collect the data, are we required to use you for the processing?
Nope, no, that's really up to the customer, in terms of the level of processing they require from us. And, we perform data collection only projects all the way through just providing the extracted content, kind of what I was talking about on that telco one with the 5G antennas. So it really depends on what you want as a deliverable. So we're pretty open as to really how we can support the various projects that you have.
Great. How many miles a day can you collect, capturing both LiDAR and imagery?
So, with the Simbo device, we can collect about 60 linear effective miles per day. So each vehicle will actually collect about 150 overdrive miles. No, hang on a second. This just shows you. So this is one of our drivers. All right. And you can see back and forth. So there you have overdrive there, overdrive on the exit ramp, overdrive again. So, we're collecting a lot of area, but there's a lot of what we call overdrive. All right. But again, our plan is to have 70 of these sensors in action. So when we're not doing paid for mapping projects, they'll be on the street doing data collection on spec. So again, we're building this archive of data over the top, initially the top 100 cities in the US, and then that data will be available via a data as a service model online.
Great. We perform imagery and LiDAR data collection with various platforms, including mobile, manned aerial, and UAVs. Can you provide the processing and automated extraction of data that we collect?
Yeah, we can. So, the voxelization of the content and the processing, classification, and extraction can all be performed on virtually any data set. So it really doesn't matter. And so, I would just suggest, you can reach out to me after the event. You can stop in the networking lounge. I'll be there for most of the day. And we can talk about doing a test or proof of concept for you.
Great. I like the high definition maps you can create with your Simbo system. However, I also need to collect top-down views of some of my assets. How can you collect both?
Good question. Good question. So, when you think about the utility distribution network, and looking at damage to, say, cross arms, right? Can't necessarily see that damage on top of a pole from rot, right, from the top of the cross arm. So we have strategic relationships with both manned, aerial, and UAS-based data collection organizations, strategic partners. So we can consume a wide variety of that rich sensor content that they create from various platforms, and then we utilize our VMAS software to process and manipulate it. So really, again, it doesn't matter where the data comes from, we can still consume that. And again, we have partners that support us in some of our project activities.
Thanks. How does Voxelmaps address the challenges with data delivery in terms of file sizes or formats?
So, the one of the challenges of this high resolution remote sensing data is file size, and be able to actually use the data instead of just having a pretty picture. So we have a variety of software to ensure that we can deliver in the correct formats. So, like I said, Autodesk and Esri or MicroStation, whatever you're using, and then we can customize the size of the files that we deliver to make sure that we give you the file sizes that map into the software you're using, as well as your project size. And as I mentioned before, so we're doing this digital twin of the planet, right? And so that data that we're collecting as part of this ongoing process will actually be available online via data as a service. So you'll be able to use OGC compliant calls to be able to call and access feature services to deliver that content directly into your applications.
And finally, with automated sign inventory, what is your margin of error for identification and rate of collection? And what is your rate of collection?
Yeah, so with solid training of the algorithms on those particular signage, that one in particular was at the 98th percentile, is what I was told. So that was a project done before I arrived 90 days ago. But the average or the accuracy was in the 98th percentile. So again, it really depends on the training of the algorithms to know what feature it's looking for, right? And that's the holy grail of every AI ML tool out there.
Well, thank you very much, Brian. Looking forward to having you later in the panel. And now it's time for our next presentation.